Okay, thank you very much. I want to thank the organizer to give me this opportunity to speak. Um, and thank you for the introduction. Today my topic is quantum critical K-theory. So yeah, I apologize if you heard this many times because it's not so recent work. Um, so I will gradually explain what is quantum, what is critical, and what is K-theory in my talk. So I will start with explaining what is critical locus. This word, just critical. Okay. So start with X to be a smooth variety over C, and I consider regular functions on my variety X. So you can think that X is alpha in space Cn, and phi is some polynomials. It's very basic objects. And then what is the critical locus? That's by definition, that's the zero locus of derivative of phi. So which means that you consider this Pull-by diagram where this X to cotangent bundle of X by zero sections, and the other sections given by the graph of this derivative of phi. Okay. And the critical locus is the intersection of these two submanifolds. So potentially, because this phi is general and this intersection is not transverse, so critical locus is in general not necessarily smooth, so it could be singular. And also another feature is that the critical locus could be non-compare space. So it could be both non-compare and singular. So although the ambient space is nice, the function is nice, the critical locus maybe not that nice. So associated with such a data, X and phi, we can consider so-called category of B branes in this world of mirror symmetries, 2D mirror symmetry, more precisely. So the category of B branes in this setting is the so-called coherent matrix factorizations, which I denote here this matrix factorization category to be the quotient of this homotopy category of factorizations module this cyclic objects. So particular, this category consists of objects of this form, where this E0, E1 is a pair of coherent sheaves on X, on this ambient space X. And there are morphisms between these two coherent sheaves. We call it D0 and D1. So they are required to satisfy this constraint that the composition of both sides, they are almost zero, but it's not exactly zero. They're the same as multiplication by the function phi. So in particular, if function phi is zero, you can turn this make it to be a periodic 2 complex. You put it E0, E1, E0, E1, you put D0, D1, D0, D1, then this is exactly complex of coherent sheaves. So that's why I say this when function is zero, this is some Z2 version of this Dirac category of coherent sheaf of X. Okay, that's the category of category of B branes we are interested in. So this is a category. So usually you can consider some decategorifications by the following two ways. So one way is you can define so-called periodic cyclic homology of this matrix factorization categories. Then what you get is, roughly speaking, is some so-called critical cohomology. It's some Z2 version of this cohomology of vanishing cycles applies to this constant sheaf Q. So another way to take the categorification is to take the Grothendieck group of these categories. So I give it a name, this KXV, to denote this Grothendieck group. This will keep appearing in our talk, which I give a name. We call this critical K-theory. So in particular, when phi is zero, you recover the ordinary K-theory of your smooth variety X. But now you have potential functions, so we call it critical K-theory. Because everything is localized in the critical locus of phi. Okay, so typically, such X is coming from the so-called GIT quotients by some vector space by some reductive group, and this function phi is descended from this vector space. Okay, so to be more precise, we fix the setting of the remaining talk as follows. So we have a W is a vector space, and we have functions, regular functions or polynomials on this vector space. And there's an actual data called G cross F. There are two groups. G is a reductive group, and F is, let's say, it's a torus. So now the function is compatible with G and G cross F action in the following sense. So first of all, the function phi is a G invariant. So that means if you take a quotient by G, so the function descends. And it's not invariant under F, but it's equivariant under F with respect to some character of F, which is group Hom from F to C star. And let's denote this F0 to be the kernel of this chi. So by this F equivalency, you see that this function phi is actually preserved by this smaller torus, this F0. So I intentionally use G to denote this reductive group because I want to say G is a gauge group and F is a flavor group in this physical language. So that means that we want to take a quotient of W by this gauge group G. So we want to model out just G actions. So to do that, we fix the character of G. And let's assume that the semi-stable locus of W is the same as the stable locus, and such that the G action is free. Okay, we don't worry about the Stirling-Mumford stack quotients. We just consider this free quotients, and this is GIT quotients exists as a smooth variety, and as we said, this function descends there. So another data we want for twisting in the later context is this co-character of F. We call it R charge, which is group Hom from C star to F. So that's basically the data, and the requirement is that the critical locus of phi in the critical locus here after the descent by G, we require to have properness in the sense that this F0 equivalently proper, which is the fixed point. F0 fixed point of critical locus is proper. So this is the setting. So let's look at some examples. So the first example is given by so-called gauge linear sigma models. In this example, particularly, the aim is to realize quantity threefolds, this famous quantity Calabi-Yau threefolds, as a global critical locus. So how to do that? So the idea is to consider the total space of canonical bundle of P4. You can realize as a GIT quotients by C5 cross C over C star. You can choose some specific conditions so that this stable locus just take out the origin in the C5 component. And the C star action is basically has a weight 1, 1, 1, 1 in here and -5 in the C component. And this function phi is very explicit. Using coordinate here, you can write as it maps x1 to x5 and p. P is the coordinate in the C directions to p times this 20 polynomial, this x1 to the power 5 plus x5 to the power 5. So now we have vector space, we have gauge symmetry, we have potential functions phi. So we also have flavor symmetry. So flavor symmetry C star scales this W or W over G by scaling this C directions with, let's say, weight 1. Okay. So now what you can track is you can analyze the critical locus of this function phi, which you find is basically you take a derivative with respect to P, then you require to be 0. That's the equation. So what it ends up getting is this 23 volts sits inside the CP4. As I just mentioned, as a decodification of matrix factorization, categories, we are interested in two vector spaces. One is this critical homology, cohomology. One is this critical K-theory. So in this particular case, we know that by dimensional reduction, both this critical homology theory or K-theory reduced to the ordinary homology or K-theory of 23 volts. So you can say that your physicists are interested in 23 volts and they are interested in the linearization, the state space by homology or K-theory. But now you can realize there's a critical locus and you can put everything in terms of this language, in terms of this critical homology theory or K-theory. So this looks strange because originally this is smooth. You want to realize a critical locus. Why you want to do that? I want to say that this is particularly useful to determine the converting invariance of 23 volts under the name of this Lambda-Ginsburg-Calabi-Yau correspondence. Okay. Calabi-Yau refers to, you directly look at the 23 volts. LG means you look at this GIT quotient with potential functions. So this fits into our setting. So, yes. High dimensions. I think so. Yeah. Yes, I think so. Yeah. So the second kind of example is related, but it's the flavor is very different. So it comes from linear algebra. So it's called quiver with potentials. So the setting is you draw this quiver diagram, which is an oriented graph. Okay, there's a vertex. There are paths between vertexes. So in here, we consider one vertex and 3 loops here. And then we consider another vertex. We use different labels to emphasize this is a framing a vertex. We consider a path from this framing to this gauge node. So now you want to consider the representation of this quiver. What does it mean? It means that you put, you assign a vector space to each your vertex. Then you consider the, when you see a path, you consider the homomorphism of this vector space from the source to the target. So in particular, in this case, you see there's 3 loops. So I wrote hom V to V 3 times. And I cross a V because there's a map from C to V, which is identified with V. And now we want to model out this gauge group G, which is the GLV here, this general linear group V. And the function phi is explicit using this coordinate ABCV. So we can write as a trace of this A, B bracket C. So A, B, C, they are homomorphisms from V to V. So you can write as a matrix. So it makes sense to take bracket of B and C, B times C minus C times B. You further times A and take a trace, then it becomes a number. So this is the model, and the flavor symmetry is chosen as follows. You take a C star free, which is you scale this ABC by this T1, T2, T3, and you can consider a subtorus, which is the multiplication is 1. So why this example are interesting? So the point is that the critical locus of this function phi can be identified with so-called Hilbert scheme of endpoints on C3, where n is the dimension of the vector space I put here. So this is it's a modular of sheaf on Calabi-Yau threefolds, the simplest Calabi-Yau threefold C3. And it's non-compact because C3 is non-compact. So Hilbert scheme of points is basically the points configuration on C3. It's also non-compact. It can go to infinity. But it's equivalently compact in the sense that if you consider the F0 fixed point is compact, and it's more than compact, it's a finite number of reduced points labeled by so-called 3D Young diagrams with n boxes. You lay these 3D boxes in this 3D space, and this is give you the combinatorial description of this critical locus. So why this thing is interesting? Because if you consider the F0 equivalent critical K theory or homology theory, this is the main topic of recent study in the so-called under the name of cohomological or K-theoretical DT theory of local Calabi-Yau threefolds. So in this example, this local Calabi-Yau threefold is just C3. And they are extensively studied by many people like Serge Soberman, Davidson Manhart, Padararu told us. And what's more, it's such vector space is interesting in the sense that they are the natural space to do geometric representation theory. So people like Rabchak, Soberman, Yang, and Zhao, they construct some quantum group actions on this direct sum of vector space. So the third type of example coming from so-called Nakajima quill varieties. So the things I want to say here is any Nakajima quill variety can be realized as a quill with potentials. So quill with potential is more general. So let's look at this particular example. You consider this a one gauge node and one frame node. So we put some numbers here. You put some just pass between this node, and you put a loop there. Consider the representation of this quivers, which is given as here, because just consider home from here to here, here to here, and here to here. Then you consider the particular potential to be the trace of this b times a times epsilon, but you just take a multiplication of the epsilon many times. Let's say L times. Then you can put some flavor symmetries, F to be the torus inside this GLN here, and also some extra torus scale in this A and epsilon. Okay. You choose some character chi. Then you can analyze the F0 fixed point of your curricular locus. And this is finite number of sets, and the number of points here is exactly the dimension of, or rather, you can take a sum of n here, small n here, then the dimension is exactly the same as the capital N's power of this L symmetric tensor of C2, this vector space. Yes, this is more general. So this comes to the second page. So the critical homology gives so-called highest spin representation of SL2. And when L equals 1, as Yehao mentioned, so this critical locus become Nakajima quill varieties. Particularly, this is cotangent bundle of Grassmannian. And this two vector space reproduce you the ordinary homology or K-theory of your Nakajima quill varieties. So the point is that Nakajima quill varieties is a strict subset of this quiver's potentials if you increase your L. Okay, so having so many examples, the question is, or the main topic of this talk is, how do we assign quantum corrections to the setting, so to X with a function phi? So what I mean by quantum correction is I consider the critical locus of this function phi. So I intentionally draw this picture in an ugly way to emphasize this potentially can be very singular. So what I mean by quantum corrections, I mean is I want to count maps from some Riemann surfaces with mark points to my critical locus. I want to enumerate number of maps from curves to algebraic curves or Riemann surfaces to my critical locus. So I want to say this is non-trivial because critical locus could be singular. So there's no direct way to count this as the ordinary homomorphism theory, because quantum theory deals with smooth ambient space. So the idea is you consider some twisting maps. So this uses the data of this character and co-character, this chi and r. So let's see how we do this. So let's say we fix a domain curve first. We fix a pre-stable curve C with mark points P1 to Pn. So I want to consider the mapping stack from this particular curve C to the critical locus phi over this G cross C star. So now I want to map this mapping stack to another mapping stack, which I map this critical locus to a point. I forget the G actions, and I map C star to C star by the composition of R and chi. I call it R chi. So now the target is the classifying stack of line bundles or C star bundles on the curve C. So I want to fix a particular point here, given by this log canonical bundle, which is the ordinary canonical dualizing line bundle of curve C, adding this divisor pi, this mark points pi. I fix this particular line bundles. Now I define this twisting map as this fiber diagram, which is as a point here, such that the C star data is fixed by this omega log. So let's look at what is the particular point. A particular point here will be what? Will be a principal G cross C star bundle. And this principal G cross C star bundle has a G cross C star equivalent map to your critical locus phi, which sits inside W, such that it satisfies this twist condition. The C star line bundle, the C star principal bundle, after base change by this R chi should be omega log. I just literally say what I mean by this diagram. Okay? So for such a data, you can talk about a curve class. What is a curve class? That's a homomorphism from character group of G to Z, which means you take a character of G, which is a G cross G. It's a map from G to C star. Then you consider this. You have a principal G bundle here. You consider representation bundle of this G on this by this character. You get a line bundle. You take a degree. This is the curve class. So now in general, you know that this mapping stack is not good in the sense that the automorphism group is big. So if you work with such things, we are forced to deal with so-called Artin stack. But in general, there's a way to choose a nice substack called a quasi-map. It's a big condition due to the work of Fontaine, Bansi Kim, and Davish Malik. So it has some particular definitions, but one key thing is that they require the image of this map U to sit inside the stable locus of critical locus of phi, or rather, it sits inside the stable locus of W except finite number of points. So now we can consider so-called quasi-map moduli, which means I replace C, a particular curve C, by this family of curve. This is a moduli style pre-stable curve. This is a universal family. So I replace C by this family, and I imposed the similar twisted mapping style constructions, and I impose this quasi-map stability, and you get this. I just give a notation. This quasi-maps Gn, genus G unpointed, with this twist R chi equals omega log to the critical locus, and with some curve class beta. Okay. So the remark is that this is a finite type separated DM stack, so it's pretty nice to do integration theory, and is moreover compact in the sense that the F0 fixed point is proper. Okay. This follows actually from the critical locus is F0 equivariant proper. So I want to say that the similar moduli space has been considered in the when F is C star case used in this GRSM case or FGRW case. So here we allow F to be higher rank torus, deal with this non-proper critical locus case. So let me give you an example of this cosine maps to critical locus. So let's consider the Hilbert C3 examples we just mentioned before. So we consider this particular R and chi given by this map, where this R is you map C star to C star 3, you map T to T to power sigma 1, sigma 2, sigma 3, and the chi is given as before. So now, what is the cosine maps? So now this is a parameterized version of cosine maps, but anyway, let's ignore that technical part. So that's cosine map can be identified with so-called moduli space of Panera-Thomas stable pairs on this Calabi-Yau fourfolds. Okay. So where X is the total space of this direct sum of these three line bundles, sigma 1, 2, 3, on P1, where the sum is -2. Okay, this is, anyway, if you are not familiar with PT stable pair, this is the definition. So PT stable pair is a one-dimensional, pure one-dimensional sheaf with a section on your X. So the point here is that here you consider a map, whatever twisted map from P1 to a moduli space of sheaf on C3. Okay, so tautology. It's like tautology that this mapping is a modular of sheaf on P1 cross C3. But now in a twisted way. So it's not exactly P1 cross C3, but this total space of the direct sum of three line bundles. So this statement make it precise which moduli of sheaf on these fourfolds it corresponds to. So more generally, you can allow mark points. So previously there's no mark points. I put no mark points here, just a P1. If you put n mark points, then the log canonical bundle is written as the following. Then what a particular cosine maps looks like, parameterized cosine maps look like this. You consider you have a disjoint component here, which is isomorphic to this P1 you fix, and with several mark points. And then at each and here you have n number of special points, and you can bubble this chain of rational curves. And by stability condition, in each last component of rational curve, you need to have a mark points, so you can evaluate these mark points. And such a data is mapped to the critical locus over G. So in this relative settings, you can try that this twisted cosine maps with mark points exactly correspond to so-called relative stable pairs on this. It's not necessarily Calabi-Yau fourfolds, but it's a fourfolds with its anti-canonical divisor. It's a log Calabi-Yau fourfolds. Okay, so now we come to this the central part of the difficulty of defining this count. The difficulty, as I said earlier, is comes from the fact that critical locus is not necessarily smooth. So there are many previous approaches to such problems. The main point of all those approaches to use the smooth ambient space. So critical locus sits inside this smooth ambient space X, and then they try to localize to the critical locus. So there are so many names here, so you can see. I hope I didn't miss your name. But here, the point is that our approach is different from the previous approach in the sense that we directly work with the critical locus. We don't need this ambient space, and we use the framework of so-called shifted symplectic geometry of Alternative poem by K. Visossi. So what does it mean? So we start with a smooth variety X. So you can consider the cotangent bundle of X. So we know this is exact symplectic manifolds. Then given this regular function phi, so we have two exact Lagrangians. One is this 0 is given by 0 section. The other is given by the graph of d phi, as I said before. So now, as the critical locus, as critical locus is realized as the intersection of these two subvarieties. But now I want to take a derived intersection, not the ordinary intersection. So the derived intersection is some so-called derived schemes, and it's pretty nice in the sense that it has shifted symplectic structures, so-called -1 shifted symplectic structures. So what does it mean is there's a notion of unshifted closed two form, which you can use it to identify the tangent complex and the cotangent complex up to a degree shift. Okay. So that would be your shifted symplectic structures. And in this particular case, this is -1 shifted because there's some general theorem says that if you consider 0 shifted Lagrange intersection, it will become -1 shifted symplectic. So why we care about this? Why this is relevant to our problem? So the problem, the relation comes from the following questions. So you are, because this setting is so natural. So you start with a smooth variety of functions. You take critical locus, then you get some symplectic things, not ordinary symplectic things, some derived symplectic things. Then you are forced to ask what is Lagrangian there, right? Because symplectic geometry is it's about Lagrangians. So you're asked what is the example of -1 shifted Lagrangians in this critical locus. There's a short answer. Let's say we fix a curve C, and let's say we fix this gauge group to be identity. You consider this twisting mapping stack I just mentioned before. But now G is identity. It's pretty easy. Then you can consider the evaluation map to the critical locus. So sorry, I should write this R and D, they are the same. Anyway, they are both derived critical locus. And in this case, as I said, this is n copy of derived critical locus, which is product of -1 shifted symplectic is -1 shifted symplectic. And actually, this map is -1 shifted Lagrangians. And in general, you can vary the curve C and your G bundles. It'll be more complicated. So let me introduce some notations. So we consider this cosine maps, as I said, to the critical locus of this function phi. So I change the notation to be phi W over G because there will be another phi in the later slides. So from this twisted mapping stack, there are two maps. So one is you forget the section data in this cosine map. Then you map to this twisted moduli stack of G bundle. More precisely, G cross C star bundle, where C star part is fixed by this omega log. And such things is further, you can have a smooth map to your pre-stable curve. In the stable range, you take a flat map to the stable Deligne for moduli space. So the other direction of map from this M is given by evaluation map. Because you have n map points, so you can evaluate your map at those points. It maps to the nth copy of critical locus. Certainly, you can embed into ambient space to the power n. So now, I want to say that this M actually factor through the product of here and here. It's not a product, it's the fiber product. It's fiber product here. I wrote it as a capital B. This is this bond data cross this ambient space data over this point over G. So this is a smooth Artin stack. And such stack B looks complicated because there's a bond here, but it has a smooth map to a very nice stack, X. Okay? X is what? X is this GIT quotient, W over G to power n, cross this the Riemann for moduli space, this stable curve with mark points moduli space. So this is a global quotient stack. It's pretty nice. And you have a function on this smooth stack B given by this pull-by diagrams. Okay. This function is the same as you first project to this x, and then in x and in here there's a natural functions given by the function you start with. You start with a vector space, a gauge group. You have a potential function there. You can take a so-called direct sum function on here, which is you map x1 to xn to the sum of phi applies to this xi. Okay, and this function has nothing to do with this curved component. Okay, so this is the start with our cosine maps. This is what we get. So we abstractly write it in this way. So you have a stack M. You have this M can be very singular, but you have a smooth stack B. The smooth stack B has a flat map to another smooth stack. It's better, which is a global quotient stack. And this global quotient stack has a potential function and induce a function here. This is data. So the next statement is with Gufang Zhao, is we show that this cosine maps to this diacritical locus of phi, of this phi, is a -1 shifted Lagrangians. Then you are asked why I care -1 shifted Lagrangians. So the answer is the following construction. We call it critical pullback. It's a joint work with Yukinobu Toda and Gufang Zhao. So what he said is, given a -1 shifted exact Lagrangians from M to the diacritical locus phi, where phi is a function on a smooth stack B. Okay. So under the condition of the following three conditions, so the first B is a smooth so-called QCA stack. It's cosine compact with affine stabilizer. And with the data that there's a flat map to a global quotient stack X, such that this function phi is a pull-by function on this global quotient stack X. And there's some technical assumption on this F and also M. Let's just ignore this for the moment. We further require that this the symmetric complex, which is the quaternion complex of F, restricted to the classical truncation, has a three-term resolution given by this VEV2. Then we can show that there's a natural defined map. We call critical pullback. It's a pullback from the critical K theory of X phi X to the K theory of your module of M, satisfying natural functorial properties. So you see that this pictures exactly fits into exactly contains these examples. So you can apply to this example. Then what you get ends up getting is the following map. It's like a correlation function or k-theoretical Gromov-Witten type invariance, in the sense that you can insert insertion from moduli of stable curve. You can insert your state space coming from critical K theory n times, and it ends up getting a number in the sense that this is in the F0 equivalent K theory point and satisfying Green formulas. So this is what I call this a quantum critical K theory, because it's the quantum K theory of this pair, or rather for this critical locus. And in particular, 1B is a point that will produce the work of O and Thomas. It also has nice localization formula, just helpful for computations. Okay, so in the final maybe 10 minutes or 9 minutes, so let me just give a sketch of construction of how does it work. So the point is the following. So maybe let me write something here. So so we consider this M. We consider this B. This function here, and this is a flat map to X. So X, remember, is a global quotient stack. Let's say this like S of H. S is a smooth quasi-projective scheme. H is a reductive group. And consider Dirac critical locus. B here. As I said, this is a -1 shifted Lagrangian. And in general, you can show that by composing these two maps, this map is so-called -2 shifted symplectic. So fiber-wise, this is -2 shifted symplectic Uriah stack. So classically, you can think the example is like the fiber-wise is like behave like modular sheet from Calabi forwards. Okay. So let's call this map F. So the aim is what? The aim is to construct a map from not the K-theory of X, but the critical K-theory to take care of the function X, Px. Critical K-theory of X to the K-theory of your M. So this is the aim. Okay? So the idea is the following. You consider this map F, you do this deformation to normal cone. Okay? So maybe, okay. Say again? Thank you. Okay. So the point you consider this deformation space of F, which is a flat A1 family, and the zero fiber is the so-called intrinsic normal cone of F, and generic fiber is the base. Okay. So now the idea is that you want to construct Kx, Px. So first of all, you can flat pull back to your B. Here. B here. Then you want to do specialization. You want to define a specialization, like you extend here, you do Gisin pullback here. This is the ordinary things people do in the intersection theory. Okay. You want to map it to the K theory of this intrinsic normal cone with some potential functions. Q. I will explain in a minute. So then it will be done. If this map is defined, it will be done because given this data, this intrinsic normal cone sits inside this vector bundle stack. So as I said, this required this coordinating complex restricted to the classical truncation. It's given by this Freighton complex VE V2. Okay. So this has a map to the coordinating complex of the classical truncation of F. So from this data, you can show that this intrinsic normal cone sits inside this vector bundle quotients. So you take a E here, smooth pullback. You take a cone here. So now this E, because this is a symmetric complex, that means E has a quadratic form, has a non-degenerate quadratic form. Just give you a functions, QE. Okay, so you have a function here. So in fact, you show that this function pull back to here descends to here. Okay? So that's what I call Q. So now the thing is, you start from there, you can pull back to here. You can further just push forward to the E and the QE. So now you're in good position because E is a quadratic vector bundle. Up to take some, let's say this is even rank. Up to take some covers, you can assume this is like lambda plus lambda 2. Then there's some Kosovo factorization here. You can take a tensor by Kosovo factorization. Pursue factorization. Then you get back to what? Get back to E0, but with support on the 0 section n. At level such, this is K of n. That will be done, okay? But I want to say that the most difficult part of this construction is to construct this specialization map. Because usually how people construct stable specialization maps, you first need to have excision. So because this is the total space, you have some open part, you have some closed part. What you want to do is if you know there's some excision sequence, you first extend your K theory, whatever K theory or critical K theory to here, then it's input back to here. But in general, when in the presence of a potential function, specialization map does not necessarily exist. Okay, so that's the difficult part. So instead, what we do is the following: we cannot pull back here, but we can pull back from here, because in here this is a global quotient stack. So matrix factorization category is the same as the so the matrix factorization category of x and Vx is the same as singularity category. So it's dB co of 0 section, sorry, 0 locus, modular perfect complex. So now in here, so anyway, we know that the K theory of 0 locus suggests to the critical K theory. So now we want to take a lift here, take a K theory in the 0 locus. Now in the 0 locus, there's no potential function. You have excision. You can do this deformation to normal cone. Then you can have that map. Then you show that the perfect complex goes to 0 under your map. So this is the way we construct it. And to show this goes to 0, you need to use this condition that, for example, you need to use this is -2 shifted symplectic. You need to have these structures. And also you need to use this B has a QCA conditions so that we have some compile generations properties for this very general smooth arting stack. So yeah, maybe just leave the last 10 minutes for questions and stop here. Thank you.
Thank you very much for your very interesting talk. Yeah, we have lots of time for questions. Are there any from the audience? Maybe I can ask with a question.
Please.
Yeah, not clear how important that is for the whole theory, but you mentioned the moduli of bundles.
Yes.
And I was wondering if the sublocus or the wobbly locus somehow plays a role in this whole field.
Sublocus of what?
Wobbly bundles. Those bundles who admit the nilpotent Higgs fields. This showed up at some point.
In my setting, there's no Higgs field in present.
Yeah.
Let's see.
It's just a question out of curiosity. If you haven't seen it, then it's
there's no Higgs field appearing in these constructions. So maybe in the future, if Higgs field comes in, so potentially it's
maybe a somehow related question is about whether you discussed examples like Hilbert varieties and so on. Is there also an example of expanded moduli spaces which can be built with?
Let's see. So, so Higgs, how to say? Higgs moduli is something like ordinary symplectic things. Right? This is complex holomorphic symplectic. So what I talk about today is more like not ordinary symplectic, but it's shifty symplectic. So in geometry means in this Higgs bundle case, it's more like you consider modular of sheaf on some local Calabi-2 surface, Calabi-2 surface. But now what I consider is Calabi-4 or Calabi-3, or interplay between Calabi-3 and 4. So I think it would be an interesting question to study the similar questions for maybe interplay between Calabi-2 and Calabi-3. That would be interesting, maybe. Yeah.
Thanks. So further questions. So if not, let's thank Professor Cao again and
Thank you.